Okay, yeah. So we'll continue one more. We'll continue our discussion in three-phase induction motor with one more topic here. That is speed control of three-phase induction motor. Speed control of three-phase induction motor. So as speed control is very important. Okay, for any machine, because in industrial requirements we may require different speeds here. Okay, why synchronous generator or synchronous motor is not so popular and why induction motors are popular? Because of its variable speed applications here. And even in the fan which you are using here, if without regulator, can you able to simply use the fan? So for the three different seasons here, so let it be summer, winter or rainy season. So we cannot operate the fan in single mode. So we can operate in 5 different modes that we used to do in olden days. Now even smooth control has been came here. Even we can control the speed precisely here. If I want to get the speed with 955 RPM, okay, we can control the speeds with 955 RPM starting. Okay, so this is how the speed need of speed control. Okay, so how it is achieved in three-phase induction motor, we will try to discuss here. We already know this slip formula. Slip equal to ns minus nr by ns. If I want to rewrite here, nr equal to ns into 1 minus s here. Okay, so nr into 1 minus s here. Even we even discussed about the torque formula, which we in detail here. 180 by 2 pi ns into s e2 square into r2 by r2 square plus sx2 whole square. Okay, so torque equal to 180 by 2 pi ns into s e2 square into r2 by r2 square plus sx2 whole square. This is the torque equation here, and from this we have derived so many other torque terms here. Let it be starting torque, full load torque, maximum torque. Okay, we have derived all the relevant terms here. Now here speed control can be done if from two sides here, from two ends. Let it be from stator side. There are two subheadings, I can say that. When speed control is done from the stator side, that is stator speed control. Okay, speed control is done from the stator end. There are several, again it is subdivided to several topics here. And similarly when speed control is done from the rotor side, again it is subclassified into several parts here. So we will try to discuss voltage control method. Okay, from stator side we will try to discuss. That means when speed control, when I am trying to modify or manipulate something from the stator side, that is stator side speed control of three-phase induction motor. When I am trying to adjust any modification from the rotor end, that is rotor side speed control, okay, of three-phase induction motor. From rotor end here we have rotor resistance control method, slip power recovery method, cascading method. Okay, so from stator side we have the from stator side, let's assume that voltage control method. Okay, so we have the equation here, torque equal to we have this formula here. We already written this formula here. That is torque equal to 180 by 2 pi ns into SCT square into R2 by R2 square plus SX2 whole square here. And even we have this one more formula here, P equal to omega T here. Output power equal to omega T, where omega is angular velocity. If I want to rewrite here, that is equal to 2 pi n by 60 into T here. Yeah. Okay, 2 pi n by 60. Okay, so that can I able to calculate this n term? Yes or no? Okay, yes or no? I can able to calculate n term, and simultaneously if I change this torque and keep the power constant, or so that even I can able to calculate the I can vary the speed here. So by changing the torque, indirectly I can able to vary the speed also. Okay, I am just telling you the possibilities here. By changing the torque, we can also change the speed here. Or else we have this characteristic here, torque versus slip characteristics here. When torque changes here, slip changes here. When slip changes, speed changes here. We have this formula here. That is nr equal to ns into 1 minus s here. Okay, speed changes here. So let's actually get into this subclassification topics here. That is speed control from the stator side. Speed control from the stator end here. The first one is voltage control method. Let's try to discuss in the easiest manner. Okay, how far we are able to understand, we'll try to discuss up to that extent. And so that you can able to easily attempt and remember even in the exams also. So first one is from the stator side, the voltage control method here. From the stator side voltage control method, okay, That is, we already have this formula here. Torque equal to 180 by 2 pi ns into s e2 square into r2 by r2 square plus sx2 whole square. Here, do you have this e2 or not? What is e2? Here e2 is nothing but EMF induced in secondary, or to be more specific, in three-phase induction motor it is rotor. Okay, na? To be more under standstill condition. Okay, under rotor, let's be generalized here. EMF induced in the rotor here. So now here, how the EMF is generated here? Is it because of the E1 the EMF is generated or not? So what is E1 here? EMF induced in the stator. So EMF induced under the stator here. Okay, EMF induced under the stator here. How this EMF is induced in the stator here? Because of supply voltage or not? So can I conclude that what is the major responsible component for the generation of E2? That is E1, which is mainly depending upon V1 here. So can I conclude here? So instead of E2, can I write, or can I replace it with V? Instead of E2, can I replace it with V here? So I can conclude that torque is directly mainly depending upon S into V square. Torque is mainly depending upon S into V square. That means when voltage changes, torque also changes. When torque changes, speed can be varied. Okay, when torque changes, speed can be varied here. Last one. When torque changes, speed can be varied here. So in supply voltage control method, in stator voltage control method, what we are doing here? Simply from the torque equation, when I am controlling the voltage, torque changes, and similarly speed can also be changes here. This is how the simple conclusion here. So just quickly copy what you find, what you know. Fast. I hope it's done. So try to write down simultaneously just to avoid the. This is voltage control method here. So here there are two possibilities here out of this. So what are the two possibilities here? So when voltage changes here, what are the two possibilities here? Voltage can be increased and voltage can be decreased. So for this wire, what is on the above here? What is that? The above wire, which I can directly hold, though the current is flowing here. Insulation. That means if the voltage is 230 volts, then the insulation or breakdown strength, the better word, there is a separate subject, high voltage engineering here. The breakdown strength of that cable wire, the insulation is more, let it be more than 230, that is 260 or 270. It won't be 1000 volts. So just to maintain minimize the cost, they will try to set the suitable value of insulation strength here, that is breakdown strength here. So such that though the current flows or the voltage flows here, because of the insulation, we cannot able to experience the current or potential difference, and so that the current flows here. So similarly here what happens here, if I increase the current voltage level at the input side, so now the insulation of this cable is 260 volts. Now I'm increasing the voltage from 230 to 300 volts. Will the insulation strength will be capable to balance that voltage? Yes or no? Already the fixed voltage is 230. Okay, and that's why the insulation of that cable is given as 260 or 270. Now by some means I am increasing the supply voltage to 300 volts. Now will the insulation voltage change automatically? No, it won't change here. So it is by default, again, it's fixed value which is 260 here. Already the voltage is 300 volts and installation strength is 260. Okay. So then automatically here installation failure will take place. Okay. Installation failure will take place, and once we touch that, we can able to experience the shock. This is how we'll get an electric shock here. Okay. So if the supply voltage is more and if the installation strength is less, then the installation breakdown will take place, and because of that we can experience a shock. Okay, or else voltage breakdown will take place. Directly we will be in contact with the live wire here. Otherwise the insulation is protecting us from in contact with the live wire. Okay. Now, so which is already once the system is designed, once the system or machine is designed here, already the suitable insulation is already done. Yes or no? Insulation strength for 315 volt, for 415 volts, let's assume that if it is for 415 volts, if it is some then around 450 volts of insulation will be done here. Okay, 450 or 500 volts. Now here if I increase the voltage beyond that, then what is happening here indirectly? Indirectly I am trying to affect the insulation strength here, so that the voltage increase possibility will not be considered. Why voltage cannot be increased here? Can you just tell me what's the conclusion here? If I increase the supply voltage, then the fixed insulation which is already having the insulation breakdown strength, that may damage, that may get failure, and so that then automatically it will be leakage currents and everything will all the faults will occur here. So only possibility is I can able to reduce the supply voltage here. This is the other point that you have to note down. Okay, remember. Okay, so always the supply voltage can be increased, and supply voltage cannot be increased, and only it can be decreased here. Is that okay or not? Shall I go to the next one? Next method is frequency control method. Next method is frequency control. The last conclusion is always the supply voltage has to be reduced for the speed control. The voltage cannot be increased beyond rated value because of the already predefined voltage levels of the insulation. Okay, predefined voltage levels of the insulations. Okay. Okay. Frequency control method here. Okay, next one is frequency control here. Okay, we already know that in transformer Vmax is proportional to V by F. Okay, in transformer Vmax is proportional to V by F here. Okay, yes or no? In transformer Vmax equal. Similarly in induction motor also Vmax is proportional to V by F here, and always this Vmax ratio has to be constant. Vmax ratio has to be constant. That means if I am increasing the voltage, similarly frequency also has to be increased. Let me try to take a small example here. If V1 is 230 volts, F1 is 50 Hz, okay, then what is Bmax here? 230 by 50. Can you just tell me that? 4.6. Yes. Now in the second case here, if V2 is 115 volts, okay, F2 is 25 Hz, then for this also, what is Bmax? 115 by 25. Then also what is the answer here? Again it's 4.6. Can you just confirm, cross check? Just I am taking the half of the two values here. Obviously it has to be same here. So when Bmax is same, okay, then even I change the voltage and frequency also, there won't be any much effect on the system. When Bmax is same, okay, there won't be any change in the system here. Okay, now we have an option called voltage control method. When voltage is controlled here, in addition to the voltage, what is the other parameter has to be controlled? Frequency also should also be varied. Why frequency need to be varied? Because we have to maintain a relation. Bmax has to be constant. So Bmax is independent. Bmax is depending upon which parameter? frequency and voltage. Frequency and voltage. So I guess in the transformer, flux is proportional to V. Okay, yeah, let's leave that. So Bmax is proportional to Bmax is constant, so that if Bmax is maintained constant, then the transformer will operate in normal condition. Okay. So, and what is the drawback here? I hope you understood the frequency control method. So if I want to change this frequency, automatically what happens here, Bmax changes, and automatically then when frequency changes here, voltage has to be changed, and automatically the torque changes, and slip R changes, and speed also changes here. So you can make any manner. There are 3 to 4 possible ways how we can control the speed here. But what is the major drawback here? Now in the second possibility, what I did here, have I reduced the voltage or not? Have I reduced the frequency or not? Okay. In the second possibility, I have reduced the voltage and frequency. Now, can I able to do the same with V3? V3, which is equal to 230 into 2, that is 460 volts, and F3 50 into 2, 100 Hz. Now, for this also, what happens here? Bmax will be again 4.6. Now, can I also use this combination? Yes or no? Obviously, as per the theory concepts, whatever we say that Bmax is constant, then there is no change, there is no issue in using the speed control here. But again, you can see that voltage is increasing. Now, when voltage increases, what happens here? What is direct relevant term? Insulation. You can just simply add a term called insulation. When voltage increases, insulation gets affected, or insulation failure. The best, easiest word is insulation failure will take place. That's it. As the insulation cannot bear more than the actual value, insulation failure will takes place. Okay. So which is not possible here. This method is not possible for frequency greater than the rated frequency, as voltage needs to be increased. So again, even in the frequency control methods also, controlling below value is acceptable, but above the value is not acceptable. Next, third one is, so let's try to discuss in the easiest manner. Okay, that's why I'm just giving the conclusions here. What is the third case here? I'm repeating twice or thrice so that even you can note down the same in the notes here. Pole changing speed control method. Pole changing, we have this Ns equal to 120 A by P here. By changing poles, what happens? Ns changes or not? Ns can be varied here. Now in what way rotor speed is controlled here, we have this formula here. Nr equal to Ns into 1 minus S. Okay. When Ns changes here, Nr also changes. This is what the simple conclusion here. Okay. Ns equal to 120 A by P here. When number of poles changes here, Ns changes here. And when Ns changes here, obviously by using this formula here, Nr equal to Ns into 1 minus S. So obviously Nr rotor speed also changes. Okay, rotor speed is also changes. From each method, 3 topics is more than sufficient. They won't ask, okay. And stator resistance control method here. So it's like a stator resistance control method is. So what is this point here? It requires 3 rheostars to be connected in series in each phase of the stator winding to reduce the voltage and achieve the required speed here. So not this automatic regulator. We have this olden 5 knob regulator. What is actually happening in the internal 5 knob regulator? 5 different speeds are there. You already discussed this in detail about the 3-point starter. How you are limiting the starting current here. At starting, we are including maximum resistance. Slowly we are removing the external resistance here. Similarly here also, if I want to change the speed here, for that I can change by using which parameter here? Voltage. How, when voltage is changed here, okay, that means here this is supply voltage, okay, and this is 3-phase induction motor. Now what I will try to do here, I will try to add this three phase resistance in series with the induction motor. Now previously whatever the voltage 415 volts is there, everything is reached to directly three phase induction motor. There is no change here. Now here what I am doing here, I am introducing a new resistance in between the supply voltage and three phase induction motor. Then what happens here? There is a drop, voltage drop will take place or not? Wherever resistance is there, what is the formula here? V equal to IR. So in the next case here, what happens here? The voltage in three phase induction motor definitely will be less than 415 volts. When voltage is reduced, then automatically what happens here? Speed changes here. Okay. So this is done by using which method? Introducing stator resistance. So between the supply and between the three phase induction motor, I am adding a external stator resistances. So that what happens here? The voltage that receives to the three phase induction motor will be what? Reducing or increasing? Reducing. So that when voltage reduces, obviously speed also changes from the above conclusions. Okay. So if you write this simple concept, that is more than sufficient. You don't need to write pages. Okay. You don't need to write pages for this. Next, rotor resistance control method here. Okay. Rotor resistance control method from the rotor side. Make it as second part. Okay. Make it as second part here. Rotor resistance control method. Rotor resistance control method. Okay. So again, we'll make use of the same formula. Torque equal to 180 by 2 pi ns into S E2 square into R2 by R2 square plus SX2 whole square. 180 by 2 pi ns S E2 square into R2 by R2 square plus SX2 whole square. Okay. So ultimately, now is there any term called here? What is R2 here? What is R2? R2 stands for rotor resistance. We have two types of induction motors. What is the two types here? One is squirrel gauge. Second one is slip ring induction motor. First one is squirrel gauge and second one is slip ring induction. In squirrel gauge, there is no provision to add external or external. There is no provision to add R external. Whereas in slip ring, R external can be added or not. R external can be added here. Okay. Rotor resistance in the rotor side. These are as per the squirrel gauge rotor. And this is also slip ring rotor. Okay. So in slip ring, their rotor resistance can be added. Okay. When rotor resistance can be added here, what is the new formula here? When rotor resistance is added here, new formula will be T equal to 180 by 2 pi ns S E2 square into R2 plus R external by R2 plus R external whole square plus SX2 whole square. Majorly what we need to consider here, that means here R external, this term is more important for me. So torque is proportional to R2 plus R external. Torque is proportional to R2 plus R external. So is torque is changing or not? Okay. Is torque is changing or not? Okay. As torque is changing here, then what happens here? Speed also changes, which what we discussed from the previous cases here. Okay. From the torque slip characteristics, when torque changes, slip changes, speed changes here. I hope it's clear. Okay. In rotor, what is the heading here? Rotor resistance control method. When rotor resistance control method is, it is specific to which type? Slip ring induction motor. Okay. It is specific to slip ring induction motor, not to the squirrel gauge. Okay. In squirrel gauge, there is no provision here. As rotor resistance is added here, torque can be varied, and as well as speed can be varied here. Okay. So the benefits have been also given here, which is not squirrel gauge is not suitable here. Okay, only suitable for slip ring here. And what is the major drawback here? Whenever R external is added here, I2 square into I square R losses will be increasing and efficiency will be decreasing here. This is the major drawback here. Okay. This is the major drawback. This is the major drawback here. Okay, I hope it's clear. Any doubts? In rotor resistance method, simply add R external to the torque equation, torque slip characteristics will change, and obviously the what happens here? Speed changes here. Speed changes. Next, third one. Second one. What is the second one here? Slip power recovery method. Slip power recovery method. Okay, so in-depth concepts will be given in separate power semiconductor drives here. Let's try to discuss in short. Okay, slip power recovery method is nothing but now here the three-phase induction motor is capable of operating at what speeds? For a four pole. For a four pole, what is the maximum speed it can operate here? 1419 RPM here. Rotor speed cannot be equal to synchronous speed here. So it has a power or it has a torque which can able to operate till up to 1499 RPM here. But in practical, are we using the same amount of power? Are we using the whole power? I can use the induction motor, 4-pole induction motor for 1200 RPM, for 1100 RPM. If I am using the induction motor for 1100 or 1200 RPM, what is happening to the remaining power or torque which is capable of driving the motor till 1499 RPM? This is my question here. What is happening to the remaining torque? The motor which is capable of, the motor which is capable of, I am giving enough supply so that the motor can rotate with a maximum speed of 1499 RPM. But I am operating the motor with 1200 RPM by speed control method. Now what is the remaining 299 RPM power, where it is going here? It's simply going in terms of heat losses or I square R losses. Okay, the power is getting wasted in terms of losses here. Now there is a concept called slip power recovery. Whatever the slip power, we can say that we have that rotor copper losses. What is the formula here? S into P2. Yes or no? We have the formula here. Rotor copper losses 1 is to S is to 1 minus S here. Rotor copper losses, rotor input power, rotor copper losses, that is equal to rotor copper losses equal to S into rotor input power. We already discussed so many times, just so that I am writing in short here. Rotor copper loss is equal to S times Z of the rotor input power here. Which is depending upon which parameter? Slip. It is depending upon slip times here. This amount of power is getting wasted in terms of what? Copper losses. Okay, this amount of power is wasted in terms of copper losses. So rotor copper loss is equal to S times Z of the rotor input power. Now what we are doing here, instead of simply wasting in terms of copper losses, I will try to connect externally the rotor through some cables. Okay, through slip rings here, and I will try to extract that power. And that concept is called as, what is the heading now? Slip power recovery. What the conclusion is, if you want, you can write down in short. Okay, first let me tell you, then you can note down here. So whatever the power that is, when the motor is operating other than its maximum speeds, so most of the power is wasted in terms of rotor copper losses. Okay, instead of wasting the rotor power in terms of rotor copper losses, what we are doing here, we are collecting the power, rotor copper losses power, we are collecting the power from the rotor through slip rings, and we are reusing the power in some other place here, and this concept is called as slip power recovery concepts. Okay. It can be done in two ways. Either we inject the power, we add the power. If I want to control the speed beyond, I can add the power or I can take the power. it can be two ways. Okay, the relevant concepts in detail will be discussed in power semiconductor drives here. There are two drives are there, static Cramer drive and static Scabius drive, okay, which is not required. Now, what is slip over recovery? You have to explain into for a 2 marks question. Slip over recovery is nothing but, okay, if you want you can note down the motor which is capable of operating at maximum speed. Will you write or enough? There is no need. The motor which is capable of operating at maximum speed. Motor which is capable of operating at maximum speed. Okay, maximum speed. When it operates at lower speeds, when it operates other than the maximum speed or lower speeds, when it operates other than the maximum speeds or lower speeds, the remaining extra power which is capable of driving the motor to maximum speeds, the remaining extra power which is capable of driving the motor to the maximum speeds, will be wasted in terms of rotor copper losses. Okay, so rotor copper losses, we have the formula here. Rotor copper losses equal to S times that of the rotor input power. You can write down that formula. Rotor copper losses equal to S times that of the rotor input power. Rotor copper losses S times that of the rotor input power. Okay, that means indirectly depending upon slip. Rotor copper losses are depending upon slip here. Indirectly it is depending upon slip. Okay, by using slip rings, we can collect this extra power. By using the slip rings, we can collect the extra power. By using slip rings, we can collect the extra power. Okay, and we can feed back. Okay, and reuse the same power to the supply, or feed back the supply to the supply. Feed back to the supply. We can collect the power from the rotor and utilize in some other place, and can be utilized in some other place. This is what the slip over recovery concept is. Whatever you studied up to this extent is more than sufficient. Okay. In sometimes I told you in 3 induction generator at the starting of the classes. Induction generator, induction motor. Okay. Induction generator, it rotates at what speed? Answer. Say any other second answer. Elise. More than the synchronous speeds. Induction motor rotates less than the synchronous speed. Induction generator rotates more than the synchronous speed. When I am using the motor here at 1470 rpm, now I want to bring the motor to the 1580 rpm. Normally, you are riding your bike with 50 kilometers per hour. If you want to increase the speeds, what you are supposed to do here? You will increase the accelerator, so that fuel consumption will be increased. So that what happens here, it takes more power, and the speed increases from 50 kilometers to 60 kilometers. Whereas in induction motor, now I want to increase the speed here above the rated speeds, so that here the maximum capable speed of the induction motor is, for a 4-pole machinery, if it is 1500 rpm for synchronous speed, 1419 will be maximum. I cannot increase further. Now I can add external supply from the slip rings. I can add external supply to the slip rings, so that additional power is given to the induction rotor. So that instead of rotating at 1499 rpm, even the speed can be increased further. When the speed increases greater than the rated speed or synchronous speed, the motor will convert as a induction generator. So in induction generator, slip power recovery concept or power injection concept will take place. Okay, let's try to write down in short here. In induction motor, slip power recovery concept takes place. Slip power recovery concept takes place. Induction generator, slip power. Okay, power is injected to the rotor circuits. In induction motor, slip power recovery concept takes place. Induction generator, power is injected to the rotor circuits. For the both the power is injected to the rotor circuit. For the both the cases, what happens here? Ultimately, you are going to control the speed here. For the both the cases, you are going to control the speed here. So this is a bit complicated. Okay, I guess we'll try to simplify things here. Cascading the two induction motors here. Okay, so when two induction motors are connected, okay, then one will be slip ring induction motor and other will be a slip ring induction motor or squirrel cage. One has to be slip ring because slip power recovery has to be done, or else the power has to be injected. Okay, this is the corresponding diagram. Simply note on this diagram. Okay, here motor 1 will be slip ring induction motor, the motor 2 will be squirrel cage or SRIM, slip ring induction motor here. Okay, when two motors are connected in cascading here, there are these are the possible combinations. Okay, these are the possible combinations here. Just you can this formula is more than sufficient here. The resultant formula, okay, synchronous speeds are possible here. When synchronous speeds changes here, then what happens? Okay, NR equal to NS into 1 minus S. When synchronous speeds changes here, corresponding rotor speed also changes here. When both are cumulative cascading, cumulative means additive. When both are differential cascading, it is 120F by P1 minus P2. What is P1, P2? Poles of the first machine and poles of the second machine. Okay. Okay, when only motor 1 is operating here, that is 120. Only these two formulas are very important. It may be, you can able to see in this competitive bits also. Okay. So this is what the concept. This is the cascading of three-phase induction motor. So we discussed in detail about the which topic here? Speed control of three-phase induction motor from the rotor side as well as the stator